Okay, let's take a look at depth first search. And first, we're going to look at a description of the algorithm. So if we pull up our slides, we get a description of depth first search over here. And so basically, depth first search is a way to search through a graph, starting from a start vertex, and it uses a like scene array or vector or list that is going to keep track of whether or not we've seen a node before. And it's going to start this off by first adding the start of the graph to the scene vertices, so the scene list, and it's going to iterate through the graph by popping from the stack, and if the vertex has not been visited, then it marks it as visited. It prints it and it processes it, and then once it processes it, it does that by looking at its children, and then adding those children onto the stack. And so we're gonna just go through a quick implementation of that. We're gonna go through it with the whiteboard first. So this is a graph, and as you can see, it's a collection of nodes and edges. And we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this list is going to be our scene list. So we'll mark this as seen, or visited rather. We'll do visited instead. So we're going to initialize all these to false because in the beginning we haven't gone through any of these edges or any of these vertices, and so we haven't seen any of them. So we're going to assume that we're going to start at 0, and we're going to just travel through the entirety of the graph. So we're just going to search through the graph just to see what all the possibilities are, what the depth first search looks like. And so this is going to be our stack. And so initially we're going to initialize it with 0. So let's put 0 onto the stack and let's start our algorithm. So first, what we want to do is we want to we want to pop from the stack. So when we pop from the stack and the node that we're popping, so here we're popping 0. So let's pop 0. So 0 would be gone. If the node we're visiting hasn't been visited before, we will change the false variable to a true. And then we will add its children if their children have not been seen, have not been visited before. So its children, 0's children are 1 and 2. And so we're going to add 1 and 2 to the stack. And we're going to pop from the stack. So we're going to pop 2. Yeah, we're going to pop 2. So now we're currently at 2. We're at 2. And 2 has not been visited before. So we're going to change that to a true. And then we're going to add its children if its children have not been visited. So we got a 1. So we would, we would be visiting 1. But we could also just say that if 1 is already in the stack, then we're going to ignore it. So let's do that. So we're going to ignore 1, even though that might be confusing, but we already know that it's in the stack, so we don't have to search through it again. So now we have the stack of just 1. And when we pop 1, we mark it as visited. So instead of false, we're going to set that to true. And then 1 has 2 children as a 4 and a 3. So we'll add 4 to the stack, and then we'll also add 3. And now we're going to pop from the stack, so we'll pop 3. And when we visit 3, we see that 3 has not been visited before, so let's set that to true. And we check its children. So 3 is linked to 5 and 1, but we've already visited 1, so we don't add 1. So we add 5 to the stack. That's a 6. That's a 5. And then we'll pop from the stack. So since 5 is at the top of the stack, we'll pop it. And when we visit 5, we see that we have not visited 5 before, so we set that to true. Then we add its children, so we got 6, 8, 7. So let's add those to the stack. So we'll add 6, we'll add 8, and we'll add 7. And then we're gonna pop from the stack, so let's pop 7. And while we're at 7, we see that 7 is false, so let's set that to true. Let's set that to true. And we'll check its children and to see if it's either if we have either visited or if it's not in the stack. So 7 has 8, and that's it. But we already have 8 in our stack, so when we'll pop from the stack again. We'll pop 8, and we'll visit 8, and then we'll see 8 in the visited table. We haven't visited, so let's mark that to true. Then we add its children, so 8's child is 9. So we add 9 to the stack. Sorry. Yeah, so we add 9 to the stack, and then we'll pop it. We'll check 9. And we see that 9 has not been visited before, so we'll set that one equal to true. And then 9 doesn't have any children that we haven't visited, so we won't be adding anything to the stack, but we will be popping from the stack. So we'll check out 6, and 6 has not been visited before, so we'll change it to true. And 6 doesn't have any children that we can add that we haven't visited before. And so we delete that from the stack. And we also check 4. And 4 doesn't have any children that have been visited before, but we're also visiting it for the first time, so we're going to set that equal to true. And that will be how we traverse through the array. So as you can see, we kind of, when we get to a point where we can search through a branch, we search through it like this, in the sense that we're gonna keep, like, even though we could have taken this direction or this direction, we want to keep searching in a given way until we can't search anymore. So we can think of depth first search as like being able to search as deeply as possible when we can. And that's how this algorithm would be implemented. Yeah, so let's look at some of the slides and some of the code and some other examples. So we just went through a depth first search of same thing. So this, same gist. We searched here, then we searched like here, and then here, and then like here. All right. So this is the basics of the code. We have a marked or visited or seen Boolean list. So that's what we initialize these to false, and it has the size of the graph. And so that's this right here, the visited. The visited. The DFS iterations, it'll take a graph and it'll take a vertex and it'll initialize a stack. So the stack is going to start with the first vertex, like the initialized vertex. So in this case, it would be 0. And that's this. This is the stack. And then while this stack is greater than 0, we're just going to keep popping from the stack. So that's this whole process where we're popping from the stack and then we're checking it. We're doing the process. So if we haven't visited it before, we're gonna first set it to true, so that way we don't have to visit again. So we visit, and that's just marking it. And yeah. So we do whatever we need to do, whether that's printing it or doing some other stuff with it, and then we set the visited section of it to be true, and then we're going to look at its edges. We're going to look at its children, at its neighbors. So we're going to see what other nodes it's connected to, and for each one of those nodes that's connected to, if it hasn't been marked, if it's still false in the visited, then we're going to add it to the stack. And so yeah, we're gonna push it to the stack. So this is another example where we're starting at 1 and we want to find 10, and we're gonna go through the process of searching through the graph. This is the graph. These are called nodes or vertices, and these are called edges. So yeah, we're gonna have at the top of the stack 1. We're gonna pop 1, and 1 has children of 2, 3, and 4, and we're gonna push those onto the stack. And we're gonna see that none of them are the goals. But first, we're gonna pop from the stack. So we pop 4, and it's not visited. So we're gonna mark it visited because we've already visited. And we see that it doesn't have any unvisited neighbors, so we don't do anything with that, and we just pop the next node from the stack. We pop out the next node, and it's 3, and we haven't visited before, so we're going to mark it visited, and the nodes that are going to be visited, they're going to be green. And we're also going to want to add its children. We're going to want to add its neighbors that we haven't visited. So we add 7 and we add 8. And we add those to the top of the stack. So we push 7 and we push 8, and then we want to pop from the stack, so we'll pop 8, and that's right here, and we add its children. So 8 has neighbors of 11 and 12, so we're going to add 11 and 12 onto the stack. And then we pop the vertices. We pop 12. And then we also pop 11. Yeah, we've popped 12, and we mark it visited, and we see it has no children nodes. We pop 11, we see it has no children and no unseen children, so we leave it at that. So then we pop from the stack again because we're not adding anything to the stack in these 2 steps. We pop 7, and it has unvisited children of 10. And so we mark 7 as visited, and then we add 10 to the stack. And so then our stack has 10, and once we pop 10, that's our goal. So we pretty much just end there. And the path we took there was 1, 3, 8, 11, 7 to 10. And it took that path because we took a depth first search. So we went from here to here to here to here to here to here, because we want to follow paths as deeply as they can until we hit them. And so this is a C++ implementation of depth first search using an explicit stack. And for this implementation, we use an adjacent list. Alright, so this is a C++ implementation. We're going to have the number of vertices in our class. And this is going to be a graph class. So we're going to have vertices, we're going to have an adjacent list. And these adjacent lists will be a list of two vertices that are adjacent to each other. So if 0 and 1 are adjacent to each other, if they're linked together, there will be a vector of 0, 1 in this adjacent list. And so this is going to be a vector of vectors. So our adjacent list will have a bunch of these relationships with the nodes. And so, yeah, so we initialize our graph. It's going to have vertices, and it's going to have an adjacent list. And adding an edge just means you add to the adjacent list. You add to the adjacent list this relationship between these two vertices. Yeah. So yeah, vertices stores the number of vertices. Vector, vector, int adjacent list is a 2D vector that represents the adjacency list of the graph. Each element in an adjacency list is a vector that contains the neighbors of vertex. So yeah, the constructor of the graph class initializes the number of vertices and allocates space for the adjacency list. Yeah, the add edge method is used to add an edge between vertices u and v in the graph, and it updates the agency list to reflect the new edge. And so this is the DFS code written in C++. This is a little bit different than the code we saw earlier, which was this, just in the sense that it's written in C++ rather than this is, I believe, Python. So let's go back to the C++ implementation. So yeah, here we have the vector bool visited, same as always. The stack, which is named pretty explicitly, and we're going to start by pushing the starting vertex onto the stack. So stack.push start vertex. So already this is similar to what we've been looking at, where we have a visited list of true and falses, and we have a stack. And an adjacency list, what that just looks like is a bunch of lists that look like this, where it's a collection of pairs, where a pair might be visualized in this sense, where we have like a 0, 1, and that's one adjacency. But we also have an adjacency such as 2 and 1. And so an adjacency list is just a collection of these adjacent pairs. So it will just be pairs of vertices that are connected. So 3 and 5, these are connected. And so that's one of the lists in our adjacency list. And they'll just be all the pairs vertices that are connected, and that's how we're going to be representing them. Is that we just have a bunch of these pairs, and the sum total of those pairs will be a representation of our graph. And so yeah, so while the stack isn't empty, we're going to pop from the top of the stack, and we're going to set that equal to the current vertex. And we're going to process that current vertex. So we're going to print current vertex if it hasn't been visited, and we're going to set that current vertex equal to true. And while then we check its neighbors. So we check every neighbor of that vertex. So we get we check the adjacency list. We check all the pairs that all the pairs that vertex is a part of. And we check every single one of those children, and we see if we visited the neighbor, the neighbor or not. We see if the other vertex in this adjacency list, which is a bunch of pairs, if we check to see if we haven't visited them or not, and if we haven't, we push that onto the stack. And that's pretty much it. So DFS method performs depth first search traversal on the graph, starting from the vertex, and it pushes all the unvisited neighbors of the current vertex on the stack. And that's a super simple implementation. And you can see we did this very easily. This is just it's just got a stack, and it's just an adjacency list, and it just pops some stack. It marks that the vertice has been checked. Uh, and so this is an implementation. We have a graph of 7 vertices, and we add edges. So this graph has an edge from 0 to 1, from 0 to 2, from 1 to 3, from 1 to 4, from 2 to 5, and from 2 to 6. And it prints the traversal starting from vertex 0. Yeah, so yeah, that's pretty much that for search. Thanks for watching. I will be covering breadth first search in a moment.